Hello, hello, welcome. What is happening? Yes. Yes. What's happening? Today, we're going to get back to what I was doing last time, which is somewhere around here. Last time was I was talking about the 7 natural notes. So the white keys on the keyboard are the 7 natural notes, which you could say C, D, E, F, G, A, B, C. And then you have the other 5 notes, C sharp, D sharp, F sharp, G sharp, A sharp, which are the black keys. And those make up the 12 keys altogether. So 12 notes, 12 keys. And the piano essentially is considered a equally tempered instrument, meaning that the notes are evenly distributed. The smallest note is called a semitone, and that is from one note to the next. So from C to C sharp, that's a semitone. So those are the 12. You got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 13 brings you back to C. There are 12 separate notes, and what we want to do is we want to compare the two instruments and sort of give a little background. So the piano was invented somewhere around 1700. And there's a long history, and it really goes back a long time. I mean, if you go back to the original 7 notes, which we're talking about, and how they were derived, they really go back to around 400, 500 BC, probably before that, but there's records. There's writings in Greece about a guy named Pythagoras. Pythagoras was the mathematician, philosopher, and he did a lot of things in his time that were recorded. Yet we don't have anything that he actually wrote. Okay, the records, perhaps, if there were any records, probably got destroyed. But mainly, we get the knowledge of Pythagoras through writings of other people, like Plato, I think, was a student of Pythagoras. And the thing that we're interested in is that he did work on a thing called the monochord, which was like a guitar, like an ancient guitar type of instrument that had strings, and you would be able to test the vibrations and test different frequencies by moving a bridge around, okay? And essentially, he was applying math to the vibrating string, and by doing that, he was able to identify a variety of notes. Okay, so what I did here was I replicate perhaps with a process that he might have gone through, and if nothing else, to illustrate the idea behind the things that we know in terms of how the 7 natural notes were derived, right? And the strings actually are a certain length. And what I'm going to do is I'm going to try and find a good shot and show with a tape measure that you can take the tape measure and you can measure the string from the nut, right, the headstock, to the tail here to the bridge. And what you're going to get is it's 25.5 inches long, which is a standard length for a Stratocaster. And I think I have another screenshot here I could show you. And this kind of, you can see if that even comes out. But you can see 25, you see 26, 25, 25 and a half is right there, right? So, but the idea anyway is that you take a string and you lock it down and you measure it from here to here. On Stratocasters, it's going to be 25.5 inches long, usually. What you do from there is you take that measurement, and this is what they say Pythagoras did. Okay, they say that he took that measurement and divided it in half, right? And if you do that, I'm looking for a screenshot. Sorry, here it is. All right, so if you take the halfway mark, okay, what you're going to get is you're going to get 12. I think you can see that. Right, so there's the nut, right? So we're measuring from here. Let's see if we can see that. And we want to go to 12 3/4, which is half of 25. Half of 25.5 is 12.75, which is 12 3/4. And it lands exactly on this fret right here. Okay, and you can see the double dots. That's the fret. And that, of course, is the 12th fret. There it is, right? That's the 12th fret. So as a scientist, he essentially does what all scientists do, is they try to find one thing, and then once you have one thing, it helps you get to the next thing. And essentially, what did he have? He had a string that was 25.5 inches in length, or whatever they measured it in, but comparatively 25.5 inches. And then he divided it in half, and it was 12.75, right, or 12 3/4. And the 25.5 inch sound was this, right? He got this sound, and then he named it. And what we name that sound is A. We give it we represent it by A. And then what we do is we go to the 12th fret, which is where the halfway mark is, and we get this sound. And this sound is also A. It's just a higher frequency. So what he discovered was that by dividing a string in half, it will have the same tone, same note, yet it'll be a higher frequency. It'll be double the frequency. Okay, so that's actually a lot of information. And what that information is it's, you can essentially do this, right? You can go here, and you can say, all right, so what kind of information do we have? Okay, we have a string, right? The string is like this. And we'll say that that's 25.5, right, in length, right? And then we divide that in half, and we get the 12th fret, right? And that is 12.75, okay? And we're going to call it A. Okay, so what we learned from that is the string is 1, right? That's the number assigned to it, is it's 1. And then when you divide it in half, is you get two halves. So when we divided this, we divided 25 divided by 1/2, equals 12.75, right? It's very simple. Okay, but you can also take this 1/2 and you can represent it, you can call it a ratio of 2 to 1. Okay, so you have 2 to 1. So one string cut in half is 2 to 1, right? So what the mathematicians do is they say, all right, well, that works out great. You know, that's a lot of information. That is a ton of detail, and it's amazing, actually, because now if that works, you can use all the math that you know, and it's going to lead somewhere. It's going to give you information. So what they're hoping for is that they could use all these whole numbers and find out the language of the string, and by doing so, they'll know the nature of a vibrating string, and ultimately they're knowing the nature of a wave, which in nature there's waves everywhere. There's electromagnetic waves, there's light waves, right? There's ocean waves. And if they can figure out how this wave behaves, they'll know how other waves behave. So they'll be getting a look at what nature does. Here's the next one was 3 to 2 ratio, right? You can see that. And what does that mean? So now they're going to divide the string in three sections. And so the way that works is what you do is you can actually calculate it like this. You can take this calculator and you can say, all right, well, I got 25.5, right? And I am going to divide that by 3 divided by 2, and we're going to get 17, and I'm going to subtract that from 25.5 to get the measurement, which is 8.5. Okay, so you get how that works. Basically, it goes over here. I guess you can do it this way. You can say, to get 3.2, you say 25.5 divided by 3 divided by 2 equals, you get 17, and then you subtract that. If you can see that, subtract that, right? And you get 8.5. Right? 8.5. And that's really, you can keep going with the math, and there's all kinds of interesting things. But what you get with this, the measurement looks like this. It looks like here you can see it better here, I think. You can see here's 8.5 right there. And it lands on the 7th fret. Okay, so the 7th fret is here. And what you get is you get this, right, which is E. Okay, so you start with A. We got the 12th fret. We have the open string, which is A. And then we got the 12th fret, which is another A. That's the octave, right? It's double the frequency. And then when we went to the whole number 3-2 ratio, okay, the next ratio in line is 3 to 2 after 2 to 1, and you get the 7th, you get right on the 7th fret. So pretend this guitar had no frets. While you're doing these measurements, you'd be adding frets. So you'd be, let's say there's just one string, no frets. You take your full measurement, you cut it in half. That's where you put your first fret, 12th fret. And then your second fret is going to go here. It's going to go right at the 7th fret, and that's going to be E. So now what you have is you have E. And that really, in the history of things, that was a big breakthrough, okay? Because if you keep going, the measurements start to kind of fall off. They start to kind of become less accurate, right? So, and also the tones become less consonant. So when you play 1 to 5 or A to E, this A to this E, right? it's that chord. It's a major chord, and it's very consonant. Right? So that's at 1 to 5. So what Pythagoras did was he then proceeded to take the fifth of each sound that he had. Going back to this, talking about the white notes on the piano, you have F here, right? So I started with F, and I wrote out the F scale, right? So there's one flat. It doesn't really matter for what we're getting into. But what I wanted to show was the first 5 notes. Okay, so you have F, G, A, B, C, right? F to C is 5. So what you do is, on the guitar, you know, that would be F and C. That'd be the 1 and 5. Okay, so that works. And then what you do is you take the 5th note and you make that the root note. You make that the beginning note. And then you take that note and you go to that 5th note. And what you get is G, right? Then what you do is you take G and you make G the root note. And then you just keep going that way. You keep taking the 5th notes, and there's D, right? And the 5th note is A. Take A. Go to E, E, B, and B. And you end up with 7 notes. These are the 7 natural notes. And they were derived from the natural harmonics of a vibrating string. The history is the string was locked down at a specified length, and that length was cut in half. And it's just the natural, the natural behavior of sound is that when you play the harmonics, you have A, E, that's another A, that's a C, C sharp. That gives you, those 3 notes give you the natural major chord, right? So it gives you A, C, and E. And you get that through harmonics. A, C sharp, E, and another A. Okay, so the natural chord, or the natural harmonics, give you the natural major chord. Okay, so that's pretty much what we're up to here. And beyond that, we're moving towards, this is the next topic I want to go into. I think this pretty much illustrates the way the notes are derived initially. Okay, and then somewhere around the 1700s, the piano was invented, and this idea of equal temperament, this idea of equally distributing the notes, was applied to that invention, right? This next page is are the black notes, and this is really the next video. I'm going to talk about the 5 black notes and show pentatonic scales, okay, which are 5-note scales, right? And essentially, the 5 notes that are used on the black keys, right, primarily F, G, A, C, and D, right? These 5 notes, you see the 5 sharp notes, they are the black keys, okay? And that actually creates a formula. So 1, 2, 3, 5, 4, 1, 2, 3, 5, and 6, right, is a pentatonic scale. Okay, I'm sorry, F, G, A, C, D, correct. Okay, so those 5 notes. So you leave out B, you leave out E sharp, which is actually F, and you leave out F. F sharp you already have, right? That is a major pentatonic scale. And then also contained, this is kind of interesting how the notes contain both major and minor pentatonic scales. The minor pentatonic is in D sharp, and that essentially is it's D sharp, G, G sharp, A sharp, and D, right? So that's kind of interesting because in the minor pentatonic scale, the third and the seventh, so this is 6 and this is 7, is actually, well, I'm not going to do that. The third and the seventh are flattened, okay, in the minor pentatonic. And the natural, this natural layout of this D sharp scale naturally flattens the G and flattens the D. I think that it's helpful to understand the science and the math of the notes. Okay, ultimately, sure, you want to create music, but you also want to be able to explore all the possibilities, all the the sonic possibilities of the instrument. I hope that's not too confusing, and have a great night, have a great day, enjoy. Thank you very much. Have a good night.